This is an atomic structure and energy review. This should help with an AP chemistry test or quiz. This has everything but periodic trends and the FRQs that might go with it. That is in the second installment. Basic stuff. Do you know the electromagnetic spectrum? Do you have this down? Do you know where everything would be? Most importantly, do you have an understanding of the center area, your colors, which ones have the greatest energy, which ones have the least amount of energy, and their corresponding wavelengths? Obviously, this is in color, so this is a little easier for you to handle, but take a moment and pause the video and place all of the energies below into the appropriate areas. Obviously, let's start with something that we are more familiar with. Visible light is the spectrum that we see. So I know that it is in color, but you need to understand that Roy G. Biv is backwards. It's Vib G. Yor. So we have to make sure that we're understanding that violet, at least according to this layout, is the furthest to the left. That means it has the most energy. And why does it have the most? Because it's closer to the left side where gamma rays are and X-rays are. Two major regions that you should really understand is after violet, it becomes ultraviolet or UV, and on the other side of red becomes infrared. Some other ones that you need to understand is microwaves. I'll squeeze it in right there, and then radio and TV. The last thing that I'd like you to understand is that this range for visible light is actually in the 10 to the negative 7th range. It is very important and useful to understand that if you have a 700 nanometer wavelength, it's in meters, is that nano is actually times 10 to the negative 9th. So if this becomes 700 times 10 to the negative 9th, that is equivalent to 7 times 10 to the negative 7th, because you'd move the decimal point 2 times back to the left, which takes that negative 9 to a negative 7. Hope you did well. Next question. Calculate the frequency of blue light of wavelength 450 nanometers. So there we are again. We have something that has nanometers in it. So let's talk about this a little bit. Frequency is our nu, right? Wavelength is our lambda. So we have this relationship right here. Speed of light equals wavelength times frequency. We rearrange that, and we would have frequency equaling speed of light divided by wavelength. Now we just need to simply plug this in. So speed of light approximately is 3 times 10 to the 8th meters per second. And wavelength, you've got to make sure you have this correct, is that nano is times 10 to the negative 9th. So that becomes 450 times 10 to the negative 9th meters. Plug all that in. And I get 6.67 times 10 to the 14th hertz. Reminder, hertz. If you're forgetting your units, that is equivalent to 1 over seconds or inverse seconds. It's all the same. So it's a pretty basic, straightforward frequency wavelength relationship for a problem. Little energy. It takes 6.72 times 10 to the negative 18 joules of energy to remove an electron from an unknown atom. What is the maximum wavelength of light that can do this? I'd like you to pause this video and think about how you'd go about this. I'll give you one little quick hint before we pause it, is think about the fact that you are given certain values. This is your energy, right? It says it takes that much energy to remove it. What is the maximum wavelength? So I have energy, I want wavelength. How could I do that? Please pause and try to determine the equation and your answer. Hopefully you thought about the equation energy equals hc over lambda. That results from two equations. Energy equals Planck's constant times frequency, and then frequency itself equals speed of light over lambda. You combine the two, and it becomes that equation. Do a little rearrangement. And that's the equation we're talking about. So let's do a little plug and chug. Plugging in the values, two constants, and my energy would look like that. And after calculating, you get 2.96 times 10 to the negative 8 meters. Just a quick question. What would that be in nanometers? Well, if nanometers is times 10 to the negative 9th, and I'm in times 10 to the negative 8th, doesn't that just slide over 1? So doesn't that just slide over 1 time? I know that's not the question, but you should be able to convert something like that. Hopefully you did well on that one. Next question. A carbon-oxygen double bond in a certain organic molecule absorbs radiation that has a frequency of 6.0 times 10 to the 13th hertz. Now you have 4 questions. I'm going to let you figure these out, but I want to talk about A and B before I do. It says, to what region of the spectrum does this radiation belong? And B, what is the wavelength of this radiation? I'll continue on for a moment. What is the energy of this radiation per photon, per mole of photons? And lastly, a bond in a different molecule absorbs radiation with frequency equal to a different value. Does this radiation give more or less energy? So we'll talk about that as well. So A and B, I'll give you a little hint, are slightly related. So I'd suggest pausing it, figuring out what you're given and how you do this. In case you're confused, the region I'm talking about is on the electromagnetic spectrum. So give it a pause and see what you can do. If you remember the electromagnetic spectrum, it is based off of wavelength. So the region is contingent on the wavelength. Most electromagnetic spectrums do not have it based off of frequency. So if I need wavelength and I have frequency, I'll do this at the same time. This is the equation that I'm using. Plugging it in, I get 5 times 10 to the negative 6 meters. Looking at your electromagnetic spectrum from earlier, you'll remember that visible light is times 10 to the negative 7. As we move to the right of the electromagnetic spectrum, as we move to the right of it, wavelength gets larger. As we move to the left, frequency and energy gets larger. So it's just to the right of visible light. So to the right, it's VIBGYOR. So that means red is to the right. So that means that this then will lead into infrared. Letter C. What is the energy of this radiation per photon? Per photon. If this is kind of confusing to you, recall and understand that this equation is actually the energy of 1 photon. So that should ease that question's difficulty by quite a bit. This is now becoming a plug and chug answer. Go for it. If you plug it in, you get 3.98 times 10 to the negative 20 joules. And that's per photon. Please understand, again, what are we talking about here is when an electron jumps, it gains energy. When it falls back down, a certain amount of radiation, certain wavelength of a photon is emitted. And in this case, it has 3.98 times 10 to the negative 20 joules. But now the second part of the question is per mole of photons. You have one photon. If you have one of anything, and then I ask you a mole of anything, then that's simply Avogadro's number. Pause it and see if you can alter that value to reflect a mole of photons instead of one photon. Taking your value, potentially putting it in a T-chart like this, you could say joules per one photon times that many photons over 1 mole. Ignoring sig figs at the moment, you'd have approximately 23,933 or just 23,900 joules per mole. The final question, letter D, asks if something has a frequency, molecule absorbs radiation with the frequency of that, 5.4 times 10 to the 13th, does this radiation give more or less energy? So that's what I was talking about earlier. If you are going to be relating these two, so 6.0 times 10 to the 13th, let's call it hertz, versus 5.4 times 10 to the 13th hertz. Looking at the electromagnetic spectrum, as we move this way on the spectrum towards gamma and X-ray, let's just say gamma on this side, and radio on this side, what we have is we have greater energy and we have greater frequency on this side. On this side, we have greater wavelength. So if my value is larger of a frequency, that means I'm further along on the spectrum to the left than 5.4. So 5.4 is not as far. I can call this 6.0. Let's call this 5.4. If I'm further to the left, I have more energy. So this value will have less energy. Now you could prove that in an equation quite easily. And what's that equation? You could simply use this and you'll get your value. But I can do that just using some logical discussion looking at the electromagnetic spectrum. Let's move on. Calculate the wavelength of light emitted in the spectral transition of N4 to N2 in the hydrogen atom. So this is talking about an electron going from the fourth energy level, right? N is an energy level, to the second energy level. So it is falling, it is dropping. So if I have the fourth level to the second level, my electron is dropping. I want to know the wavelength of that energy that's emitted as a result of that fall. I suggest pausing this and determining the equation that you should be using for it and calculate ultimately the wavelength. This may not be a one-step problem. Maybe you have to solve for two separate things to get to where you need to be. But give it a shot. See where you're at. If you're getting stuck, this is the equation that we've been working with. The energy equals negative 2.178 times 10 to the negative 18th joules. That is the amount of energy that is required to completely remove an electron from hydrogen. And then we relate it to the final energy level minus the initial energy level where the electron has either started before it absorbs energy or starts before it falls and loses that energy. So Please, if you did not use this yet, pause this now and plug in the values that you need, or else let's continue on. Plugging it in, this is what it'll look like. In the green, I've just highlighted the fact that 2 squared is 4 and 4 squared is 16. Many students forget to actually square the values, and it's very important that you're actually taking 1/4 and 1/16 in your calculations. The final answer would be negative 4.08 times 10 to the negative 19th joules. That's energy. Here is the situation, though. You need wavelength. So that much energy is released when the electron falls. So I have energy, I want wavelength. So hopefully you're ultimately thinking about an equation that we used a little while ago, where hc over E will equal my wavelength. Very important to understand that that negative is just a sign. That negative is telling us direction, so it is losing energy, but it's being released, so it still has that amount of energy. So we don't want to actually use that negative. So please plug that in and complete this problem. If you execute that correctly, it's 4.87 times 10 to the negative 7 meters. And you should be able to say, well, you know what? That is something I recognize. That could be written as 487 nanometers. So that's probably kind of starting to touch the bluish purple, bluish violet area. More blue than violet at that point, because violet is 400 nanometers. Here we go. How many half-filled orbitals do each of the following have in the ground state? This could also ask which elements are the most paramagnetic. Paramagnetic means having unpaired electrons. So there are a lot of ways you could do this. You could be drawing out orbital diagrams all over the place. So let me give you an example of what I could be doing. I could be taking oxygen and literally going, okay, I have 1s, I have 2s, I have 2p, so I have 2, 4, 6, 5, 6, 7, 8. So looking at that right there, I have two half-filled orbitals, right? 1, 2. There are my 2. And you could draw that out for each of these. The issue is that some of these atoms are much too big for that. So understanding the periodic table, understanding the blocks where the S, the P, the D, and the F blocks are, understanding the columns, that it's P1 or P2 or P3 really does help. So taking a look at a periodic table as a real fast review, please make sure you understand that these are my S's, right? So this is S1, this is S2, correct? These are my D's, so we have 1 through 10, and they're one behind. So this is my 3 D's, this is my 4 D's, this is my P block. Let's put it right on top. So this is like P1s, this is P3s, this is P6s. This is my F block, and these are 2 behind. So this is 4F1. This is 5F14. And by knowing that, you should be able to identify where each electron, the final electron, is located and be able to logically figure that out. Unfilled orbitals or half-filled orbitals can only happen more or less, unless if you're talking about an exception, where the last electrons are being placed. So you don't need to worry about inner or core electrons. You need to be worrying about the final energy level, or maybe just the valence electrons. So pause the video, try to determine where each of these final electrons are. I will do one quickly for you, just to give you an idea of what I'm talking about. Is if I look at B, boron is right here. Boron is at 2p1. So visually, what I can just simply do is, okay, it ends in 2p, and there's only one of them. So my answer would be one half-filled orbital. Let's give it a shot. Try to figure out where each one ends up and then determine the half-filled orbitals. And do it as quickly as you can, understanding the periodic table, not by drawing the entire orbital diagram. Pause the video and give it a shot for the next 5 elements, please. So I have filled where the last electron has been placed. Some of these are more straightforward than others, so let's take a look. How many half-filled orbitals are in each of these? If I look at 3p6, it appears to me that is 0. 3d5, according to Hund's rule, you always fill it up, up, up. It does not look like this. The answer is not 1, it is 5. Potassium, pretty straightforward. There is one of them there. We will skip CF for a moment, go to ZN. Going back to my Ds right here, is if I take this and I fill up another 5, this should also be 0 because Ds are full. So the tricky one is actually CF, 5F9. If you take a look at 5F9, you have 5 unpaired electrons. So you could think, oh, that's 5. The tricky part with Fs is that there is one element, either lanthanum or actinum, in this case it will be actinum, that you have to go through in the D block one time before you go into the F block, and then when you leave the F block, you go back into the D block. If you look at the periodic table itself, it does make sense. You will have a 7s right here. I'm sorry, 7s2, but then a 6d and it'll fill once before you enter. I know that looks and can be confusing, but again, if this is my CF, I have to go through here, and then this is my D before then I run through to CF. Then after this, comes back up to here. If you look at all the atomic numbers, that is the order in where the electrons flow. So this is a much trickier problem than it probably looked initially. So there are actually six, not 5, half-filled orbitals. So there you have it, using some electron configurations, determining something unique about each of them. In this case, talking about half-filled orbitals. In which orbital would an electron have a greater likelihood of being near the nucleus? So we're talking about being closer to the nucleus. You need to understand that the periodic table itself actually guides us through this. If you simply follow the blocks and the energy levels, again, each period signifies the energy levels, and then each block signifies what sublevels we are using. You should be able to determine this. Each sublevel, even if it has the same energy level, is further or closer to the nucleus. So for example, just going in order, and I know this is going to be very elementary in my drawing, but this would be the order in which we are slightly increasing distance. So here's my example that I wanted to show, is that even though 3D has a third energy level, it is further away slightly in distance than the 4s. Both with energy and in distance, 3D has greater of both. And I can determine that just based on the order. So right here is my 4s. This whole block is my 3D. So all you need to do is find the 4s and the 6s. Whichever one comes first on the periodic table will have a greater likelihood of being near, closer to the nucleus. Pause the video and try to determine which one would be the proper answer. So let's take a look. This is my 6s. That's my 4f. You need to be very aware that these are connected. After the 6s, I go through the 4f. So the 6s is first. So the 6s should have a lower energy, and in that case, should be closer to the nucleus. All based on the periodic table. Hope you did well. Provide the noble gas configurations for the following. It's very important that you're understanding how to do these, and it should not be taking you a ton of time because, again, you will understand how it works on the periodic table. A quick review on this is that we take whatever element we have on whatever period it is, and what we do is we look at the previous row, previous period, and the noble gas that's at the end of that period. And we use that to basically include all of the electrons that are more or less the core electrons, the inner electrons. And then we have to place and write out the electrons that are on the final row, or usually the valence electrons, the outer electrons of that atom. So I'm going to do 2 quickly, and you're going to do the other 4. So calcium. First, it's important that you are understanding how many electrons, and I'll show you that on the next one, that I'm using 20 electrons. That's calcium. That's right here, right? So if I'm on the 4th row, and I'm going to use calcium, what I need to do is look at the 3rd row's noble gas. So I will say argon. And by the way, just underneath so you understand, that's using 18 of the 20 electrons. I don't actually write that, but that is what is being counted in that. So now all I need to do is get the rest of the electrons. So I need to go through potassium and calcium ends. Again, the more you understand this, the first column is S1, the second column is S2. I'm on the 4th period, so that's just simply 4S2. Voila, there are my 2 other electrons. That equals 20. So there is my calcium. What I want to do a little comparing and contrasting very quickly is that what happens when you have something like magnesium 2+. So magnesium itself is number 12. But with 2+, what does that mean? Is that 14 electrons or is that 10 electrons? 2+ means that you are 2 more positive than negative, so that means that we'd only have 10 electrons. So as much as you want to say that magnesium is here now, it's actually electronically there. So it's acting like, with its electrons, more like neon, which is number 10. This is not okay. That is not okay. You cannot just drop an element and then write nothing. So what you need to think about is the fact that if you are now on the 2nd row, you need to go to the noble gas that's on the previous row. So we will say helium, and now we need to utilize all of the 2nd row to get to the point that we need to be. So that first circle, that's the 2s2. The second one is 2p6. And helium counts as 2, and then you have another 2 and a 6. 2 plus 2 plus 6 is 10. So pause the video, work on Br minus, Ag, Os, and Ni, and try to determine their noble gas configurations. Pause, please. Let's take a look at these. So bromine, if it's Br minus, you'd have 36 electrons. So now you are located where Kr is. So you would need to add an extra electron. So you'd still use Ar because it's on the previous row, and then you simply go through 4s2, 3d10, 4p6. Silver is a little trickier. So silver is right here, and you'd probably think that you do Kr, which is great, and then 5s2, 4d9. Unfortunately, this is an exception, and you need to recognize that D4s and D9s are 1 away from either being half full in their sublevel or completely full, and this is an exception. So it actually becomes 5s1, 4d10. It steals an electron from the 4s, or the 5s, excuse me. OS. A little trickier. OS is in the middle of the transition metals, but it's on the 6th period. So because of that, you have to deal with all the S's. You have to deal with the whole row of an F, and then you have to come back in through the D's. So this would be the result of that. You do xenon, and then 6s2, 4f14, 5d6. Final one, nickel. It's number 28. It's in the transition metals as well on the 4th period. The trick with this one, if anything, is understanding again that you have an S and a D that do not have the same energy levels in them. So that'd be a 4s2, 3d8. Hope you did well. Final questions. Identify the following atom based on the photoelectron spectroscopy, so the PES. What is the location, electron configuration for the electron found for the electron with a binding energy of 1.31? Now I just quickly removed some electrons on this list, so you could easily rewind it if you'd like, but the trick is actually doing this without seeing the numbers, and I'll reveal them in a moment. Here's the initial part you need to understand, is the binding energy is the first key to all of this. On this side, it's the number of electrons. So sometimes they'll have a guide, sometimes they won't. But you won't need it because, again, we have to have an understanding that as electrons fill up orbitals and sublevels, that they are completely maxed out and they move on and fill the next level, off-bow principle, filling the lowest energy available. So you have to assume that electrons are filling the lower levels, and you have to have trust that those peaks resemble that. So what you need to do is figure out which one is your 1s1. Which one is going to be the 1s1? So you need to find, I'm sorry, not your 1s1, you're at 1s2. You need to find 1s2. Where is that? So 1s2 is going to be closest to that nucleus, right? As we continue on further and further, it gets further from that nucleus. So it's going to be easier to remove. So binding energy, the greater the number, the more difficult it is to remove that electron. So I have 3 values, 52.6, 3.04, and 1.31. You have to recognize that this is signifying that it takes the most energy, the strongest attraction, okay, the most energy to remove an electron. So if that's the case, this is my 1s2. So then you go forward from that. Well, this must be my 2s2. So then this is my 2p something. And that's the trick. What is that? So they might have numbers. I mean, check this out. Technically, they had numbers on top of each other, and I just gave this all away. But if they didn't, you could gauge this. The very fact that this is worth 2, if I double that height, that's about right. So that looks like there are 4 electrons right there. If it was just a little higher, it'd be 3. If it was half of that, if it was only up to here, it would only be 1. So this looks like it is a 2p4. So if I have a 1s2, 2s2, 2p4, that equals 8 electrons, so that must be my oxygen. So that's oxygen. So have we answered the question? What is the location with the binding energy of 1.31? So if I had to answer just that, that is a 2p4. And that actually is enough for me to determine what element it is.